Hello, this is Miss Dagenford again, and I just wanted to help you catch up if you were gone Thursday and Friday. So we are going to talk about the equilibrium physiology. Now, it might be helpful to also have your ear diagrams because the equilibrium is in the inner ear, the two equilibrium senses. Now, again, if you wanted to, you can pause at this point and go ahead and jot some of the words down. And if you did that, now you can listen and just add on some things if you wanted to. So I tried very hard to make this very methodical because there are some repeating themes in the ear and equilibrium physiology that can make it easy to mix up. So I tried to really be methodical here. So we have the static equilibrium, and then we also have the dynamic. And notice I put a nice red box around some things to really draw it out. Now, static equilibrium, a nice way to say that, although it's a little incomplete, but it's easy to remember this way. Static equilibrium is when you're staying still. Now, it's not perfectly this, so I'll unpack that. So if you're just standing still or sitting down, maybe you have your head on your hand, or maybe you have your head on the table, this is going to be really helpful for positioning of your head, and then therefore you're going to know your body as well. But it'll also detect very straightforward linear movements when you get up out of your chair, when you walk across the room. But I think it's just helpful to kind of keep that staying still, just to help you remember the difference. Now, this was in the vestibule of the ear, and so you might recall we had our semicircular canals, we had our snail shell, and the vestibule was this area right in the middle. So that diagram did not turn out what I like. So if you want, you can pull out your ear diagram, and we labeled the vestibule at that point. So this would be in the vestibule, and you have these two little areas called the saccule and utricle, which both contain the equilibrium receptors for static equilibrium called the macula. Now, the macula is going to be responding to gravity, and I liken this to the plate of jello. If the ear was the wave tank, then the static equilibrium is the plate of jello. And just like a plate of jello, you can imagine this really cool tower of jello. And as you have this tower of jello on a plate, as you are carrying the plate, if you tilted that plate, the jello is wobbling back and forth. And it's responding to gravity. So that's very nice to think about. So, the organ is the macula. It responds to gravity. So, what is it going to help us respond to? Again, staying still or very straightforward linear acceleration forces. Standing up, moving in a straight line. Now, the arrangement of the macula. So again, here's something that I tried to keep very nice and methodical. The macula contain hair cells. Again, that's just a generic term. That would be cilia that have stereocilia, and that means they can move. They project and embed into an otolithic. Now, that did not come out the way I like, so let me go ahead and finish. Otolithic, there we go. And the reason they call it otolithic is because it has otoliths. Now, otoliths literally translate ear stones. They're calcium carbonate crystals. They weigh it down a little bit, and that makes it more susceptible to gravity. Now, in past years, we've talked about the difference between the utricle and the saccule, but we're not going to worry about that in terms of time. Let's talk about how this guy operates. Now, remember, it responds to gravity, so they both of them send it through the vestibular nerve. That would be a nerve that your brain interprets as then the balance. So here's how it works. When you are moving to the side, or if you're riding an elevator and you're going up and down, or just moving from left to right, or if you just tilt your head forward, when your head turns to the left, let's just say for the sake of argument, when your head turns to the left, that membrane, that gel, also moves to the left. Just like the plate of jello, you tilt the plate to the left, the jello moves to the left. And so the gel also moves to the left. Then the cilia bend to the left because remember, the cilia are embedded in that gel. So the cilia bend to the left, and then that signals to the brain, and you are going to then perceive it. It's very similar if your head turns to the right. The gel, the autolythic membrane, also moves to the right. The cilia bend to the right. This time it's going to decrease the signal to the brain, but then we perceive it as turning to the right. Now, what does this look like from a very nicer view? Here's our vestibule. I forgot I had that on that picture. Here's our vestibule, and there's our two, the utricle and the saccule, but they both have a macula. And so they both have, here's our gel, and here's our little otoliths. They weigh that down, and then here would be our cilia. And so as the head turns backwards, the gel is going to tilt backwards, and then we're going to perceive it as such. So there's our plate of jello. That one's kind of easy. It responds to gravity. So what about dynamic equilibrium? Now, dynamic equilibrium would be the semicircular canals. Boom, boom, boom. There we are. And the semicircular canals, if you notice, they're in 3 planes of space, which is really neat because think about this mathematically and spatially. You're going to be going side to side, front to back, or you're going to be spinning. So we have the inferior, posterior, and lateral semicircular canals. Now, I'm less concerned about you knowing which one's which, and I'm more interested in you realizing that it was reflective of all the movements we can do. Now, within the semicircular canals, at the base, you have an ampulla, and then in that ampulla, and I'll show you where everything is, you have the organ called the crista ampullaris. Now, a nice way for me to remember it is crazy angles. So it fits perfectly. These little guys are going at crazy angles. So where are these? They're going to be down at the base of the semicircular canals. And there, again, they're surrounded by fluid. Now these receptors respond to all sorts of movements. Like I said, you could do a cartwheel, somersault, or spin, and all of those 3 different planes respond to the movements. So that's angular rotation. Now, the way this works, and here's the annoyingly similar part, notice number 10. Each crista ampullaris contains, oh my, stereocilia that project upwards and embed into a gel mass. Sound familiar? Take a look at number 3. Embed into a gel, and then you have the cilia. So what differentiates the dynamic equilibrium? Well, it's the fact that this time it's responding to inertia of the fluid. So let's take a look at this. Number 11, here's our little star. When we rotate the endolymph, the fluid inside, it has that inertia to stay still. So when we move to the left, let's say, the endolymph is actually staying still, but it's going to move in the opposite direction relative to us. So it's going to move in the opposite direction to the rotational movement. Now, this causes the gel to bend, and then that means the cilia bends, and then they depolarize and they send the signal. So that's the real key here. So let's take a look at this, and they have a couple of diagrams which are nice and clear here. Now, I like to use the whirlpool example, so let's make sure we're clear about this. Here's our crista ampullaris, kind of the whole organ here. Here's our gel, the cupula, and then here would be our little cilia projecting upwards. And so here's what it actually looks like in the black and white. So here's our dancer, ice skater. And as our ice skater is moving, notice she's moving, look at the arrow, she's moving this way, but her fluid is moving she's moving to the right, the fluid's moving to the left. Now think about it, it's the same idea when you're coming up to a red light, green light, and it goes yellow, and you press the brakes. Well, if you're having to press hard, this car stops, but you fall forward. Well, that's the inertia that you're carrying. You want to go forward. So the same thing happens in your inner ear. Now think about what happens when you keep doing this, when you keep doing this, when you keep doing this. ultimately the fluid's going to start moving in the same velocity that we're moving in. Just like our car, when we hit speed, if we're going 50 miles per hour, the car is going 50 miles per hour, we are going 50 miles per hour. That's what causes accidents. If, injuries, when we have accidents, we keep going, right? So if we keep spinning, the fluid is up to speed with us, and then as we stop, yes, the bony labyrinth stops. Yes, we stop, but the fluid in our ear keeps moving, and that's what ultimately makes us feel dizzy, because the fluid's moving, and that's bending the gel, that's bending the cilia, which sends signal to our brain, and that's what then tells us, hey, you're still moving even when we're not, and we get a really, confusing signal for that. So, let's just recap real quickly. Here we have the static equilibrium. The organ is the macula, responding to gravity, and we have that same or similar arrangement. The hair cells that have cilia that embed into a gel. Um, but this time it's gravity which bends it in the same direction, sending a signal. And then the dynamic equilibrium, we have the crista ampullaris, crazy angles, which are at the base of each semicircular canal. This and its same or similar arrangement, stereocilia with cilia projecting upwards into a gel called the cupula. This time it's the inertia that is being detected when the fluid movement inside of our ear. When we rotate, the fluid goes in the opposite direction, which bends the gel, which bends the cilia, sending the signal to the brain. It's when we keep rotating, which allows the fluid to keep up with us, that makes us dizzy when we stop. That's what causes our senses to be getting those signals. Well, that was a bit of a whirlwind tour, but that gets us to the end of our equilibrium. Make sure you jot down some questions or watch it over if you need some help getting some things clear.